Good evening, everyone. Let me welcome everyone and also Afonso to this kickoff event of the Analytics Club called Academia to Industry. And it will basically be three parts, four actually. So the first part will be a very brief introduction, what we do in the Analytics Club and what sort of events we have lined up. And the second part will be Afonso's talk. And then the third part will be Sarah Gutt's talk from Credit Suisse. And in the end, we will have a combined Q&A session. Just a quick announcement, just to make sure that everyone is on the same page. We will record the first first and second part with Afonso's talk. And as soon as the Credit Suisse talk will start, we will stop the recording, which also means that the Q&A session in the end will also not be recorded. Okay. Without further ado, let me start with a quick introduction to the Analytics Club. You probably already know some things about the Analytics Club, but one of our main goals is just to extend the offering of ETH by showing you some insights and hosting events with company, and therefore make you a more informed data scientist. And we'll do this usually in three ways. The first one is we call it Learn. This is where I'm hearing myself. Is it from you? Okay. So sorry about that one. The first part is we basically split this in three parts. So the first one is Learn. This is where we have the more informal meetups, usually data science meetups. So if you're curious about this one, since COVID, we also started recording them, and you'll find them online on our YouTube page, which will also be the case for the first part of Afonso's talk of tonight's event. And then the second part, we call it Connect. This is like the vehicle where we reach out to companies and try to host events such as open lecture room halls or like recruiting or workshop events. So we actually want to like emphasize on the workshop events, because since we have everything like on screen, especially this term, it's nice if we have like something that is more interactive, even if it's online. Yeah, so more to this on the next slide. And the next part we call the execute bit, and this is where we have the datathon that we usually host, but this time around because of COVID we had to postpone that, unfortunately. But the Hack for Good is also one of our signature events, which is starting tomorrow. Yeah, just keep posted about these two events as well. So on the next slide, this is essentially in a nutshell explaining how our member structure works. So just a heads up, becoming a member at the Analytics Club is for free. So what is interesting and also differentiates us from other student societies is that we basically catering towards master students and also PhD students, in case you were just following, for instance, VMP or ARMIF. And what also makes us stand out of all the other student societies is that we have an admission criterion, which is you have to be enrolled at the Swiss university. And then we also ask you for some basic knowledge in some programming languages such as Python and R. And also, obviously, since our club revolves around data science and analytics, we also ask you to have a decent background or basic knowledge about machine learning and stats. Yeah, so essentially, if you, for instance, study data science, you basically get admitted right away. Otherwise, we'll ask you on the sign-up form a few more questions. Next up is our outlined agenda for upcoming events of this autumn term. As you see, we're like on the first bullet here with Academia to Industry. And then we have various other events. And again, we put a lot of emphasis on interactive workshops, which is also the case with the McKinsey event and the Credit Suisse Quant Super Day workshop. Same goes for the Schulke workshop. And we will also have another Credit Suisse, but a heavily data science focused workshop, and many more. So I would just recommend you guys to keep posted on our socials. That's the easiest way. And how can you do that? In case you aren't a member yet, here's a QR code. I will just let this slide rest for a bit because we will also upload this on YouTube. But here you also see our URL. All the necessary information you will find on there. So that was from my side about the Analytics Club itself. And I will give the word over to our moderator for tonight, which is another board colleague from Analytics Club. Stefan, let me welcome you.
Hey, thanks for the welcome. So to not let you wait any further, I will hand over to Professor Afonso Bandeira, professor at the mathematics department, and with his talk about stats and computation and network problems. So the stage is yours. We're very much looking forward to your talk.
All right, thanks so much. Let me share the slides. Okay, great. Okay, thanks so much for the invitation. It's a pleasure to speak at this meeting and to speak at the club. So I'll give a rather high level talk a bit on the very theoretical side of data science, or of even some class of problems in data science related to problems in networks. Okay. So first, I guess for this audience, maybe I don't have to explain how important data is these days. But in any case, when I searched around for nice quotes of or pictures suggesting how important data is, I found these two very nice pictures. I thought maybe it would be nice to share them. So one is a very nice cartoon picture of how these days, data can be really viewed as a resource, and it's really can be viewed as the most valuable resource. And another was I tried to see what was the value of data or of AI-powered applications, which is basically, what can be gained from data in another way. And I found a report from McKinsey and Company where they said in the next decade, this was AI-powered applications are going to add $13 trillion of value to the global economy. So I mean, to see how large the global economy is, and this is a big, this is a very considerable fraction. And of course we should try to understand what can we learn from data, what are the obstacles, what makes learning from data easy, hard, what methods work, and so on. And in particular, what I'm interested in, I mean, I'm a mathematician at heart, so what I'm interested in is understanding the mathematics of learning from data. So in particular, what are the limits of what we can learn? Like, are there things that we can learn? Are there things that we can't? Right? Which methods work and why? And here there's a very, very nice cartoon from XKCD that puts some of this in a very nice perspective, right? Which, I mean, of course, it's a caricature, but there's a lot of, especially with a lot of modern ways of learning from data, in particular neural networks, from the mathematical viewpoint, we're starting to understand more, but we really still understand very little, right? And in this depiction of you stir a pile of linear algebra until it gives you the right answers. If you replace pile of linear algebra by neural network, which is essentially a pile of linear algebra, and stir by training, it's not so inaccurate, right? Of course, there's a lot of know-how and a lot of technology and even decades of progress in knowing exactly how we should set up this pile and exactly how we should stir it. But at the end of the day, mathematically, I hope that in the next decades to come, we really understand it a lot more than we do now. Let me put it that way. Right, and of course, another way of asking what are the limits is asking what are bottlenecks. What really makes learning hard? Right, and in particular, can we develop ways of a posteriori evaluating how well we did or how we certify? Can we certify answers? None of this is very clear, I would say. Okay, so I'm going to talk about graphs and networks. So here's a graph. So a graph is just nodes and the connections between the nodes, which we call edges. right? So we can, this is a graph, you can think, say, social network, in a social network, two people and the connection if they're friends. And so let me start by asking you a question. Let's say that we get a graph like this, right? Let's say it's just a completely random, like, it doesn't even need to be random graph, but we have something like this, just a graph. And we now try to partition into two different components, say balance. So two components of the same size. And let's say we just do this at random, right? We don't, you know, we can come up with very good algorithms to cluster, but before we even come up with a good algorithm, we just literally pick out half of the nodes at random, put them on the left, half of the nodes at random and put it on the right. And now my question is, what percentage of the edges are going to be cut by this partition? So what I mean by cut by the partition is how many of the edges are going to be in between clusters or in between partitions? And so you have a thing just showed up in front of you, I think, asking you what do you think is the right answer. So how many edges will be in between the two partitions? Okay, so let's see what your intuition is like. And this, of course, you know, think of the graph as very large, as in the picture, and this in and not in an exact sense, but just rough. Okay, so maybe I'll wait a couple seconds for the answer before I give you the punchline.
Yeah, so far 8 people have already voted. 10.
All right, 10. If I'm sure, you know, probably all 10 got it right. So this is probably already, you know, already enough to. Okay, it's not an extremely precise question, so it's not even clear that, right, but.
Yeah, so the answer that are in is that 60% went for 25% and the rest went for 50%.
Okay, okay, great. So the right answer, the answer I had in mind is 50%, right? One way to see this is if I cluster into two clusters of the same size, then each node, right, will have, you know, if I look at the neighbors of each node, roughly half of them should be in its own cluster and half of them should be in the other cluster, right? Because those were at random picked to be half in one cluster, half in the other cluster. Right now, all these choices are, of course, not independent and so on, but this is roughly what we expect, and all this can be made precise, right? So if I take the number of nodes very, very large, the answer is indeed 50%. So if I pick some kind of like a random clustering, I should see roughly 50% of the edges being cut, okay? And now, so now to try to convey how sort of tricky sometimes network data is, let me give you an example. So let's say that you're reading some study of some type. It could have been in science, in technology, or trying to understand some kind of in social sciences, something like this. And you look, there's a graph, right? So the person who's doing the analysis shows to you a graph that is 3 regular. So each node is connected to 3 neighbors, right? And then they exhibit is in between the clusters is only 11%. Right? So the typical one, if this was done sort of at random, would be 50%. And here we're seeing only 11%. Right? So in particular, it's a very, very few edges are being cut. I would be at least intuitively inclined to believe that indeed these clusters, these communities, right, these clusters that are found, if it's in some kind of social network, they should correspond to communities. Like the blue nodes and the red nodes, they should really correspond to a meaningful clustering of the graph, because there's so few interactions in between them, right? For every node, there's only on average, only around 10% of the neighbors or the friends, if I'm in a social network, belong to another group. I mean, this is a very, very strong property. Okay, so, I mean, I would certainly, if I was show this would be my gut feeling. Okay, now let's move some nodes. Okay, so I'm gonna grab some nodes, I'm gonna move them. Okay, so they're moving. And now, turns out that I moved this in a way that this is another clustering where only 11% of the edges are cut, or roughly. Okay? Moreover, this clustering, as you can see by looking at the colors, is completely uncorrelated with the other one. So probably this is the meaningful clustering. Right? So how can I tell which one is better? I mean, if they cut one more edge, one less edge, they shouldn't be statistically important. Right? Here's another one that looks completely different. In fact, we believe where we believe and we know, here I don't want to make this distinction too much for now. I'll talk a little bit about this in a second. But here there's actually exponentially many for random graphs. And this is true even when the number of nodes goes to infinity, right? So this is not a phenomena of sort of low dimensions, of small graphs. The degree of the graph, so the number of nodes, the number of neighbors each node has, this 3 should stay the same. And then if I make this picture go to infinity, more and more nodes, this is still the same behavior I'm going to see, right? I can find exponentially many clusterings of where they only cut 11% of the edges, and they're completely uncorrelated, right? And this shows you that, actually that the clustering you had seen the social scientist or the scientist do for the network, actually, it's very hard now to justify that it actually has any meaning, even though it felt like it did because 11% was so small, right? So network data is tricky. And now for the people in the audience interested in graph theory, here's a very nice question. I think this is a beautiful question in this area, which is, right, remember from the question I asked the slide before, the typical cut, the typical minimum bisection, right? By bisection, I mean, I split into two even sized things. The typical one cuts roughly half the edges. Now I can ask, what is the typical maximum bisection or maximum cut, right? When I take the maximum, it doesn't really matter so much if I ask for the bisection or the cut, or I don't force things to be even. That on average will also cut around half the edges, right? By the same argument, because I'm just taking on average. And this conjecture is this beautiful conjecture that says that as the number of vertices go to infinity, then for any d-regular graph, if I take a random d-regular graph, then actually the minimum bisection will be a lot smaller than half, and the maximum cut will be a lot bigger than half, but they're symmetric in the sense that their sum is actually the number of edges. Now, because you could say, oh yeah, this is like doing this for the complement graph, but it's not, right? Because the complement graph is now a completely different object where most things are connected, right? This graph is very sparse. And so a priori, there's no reason for this to be symmetric. But however, we have I would say strong reasons to believe that this is the case. And this is open. This is a beautiful open problem in this area. So now let's try to, I gave you sort of a provocative example, but let's try to do some actual statistical study of networks. How can we try to understand when we can actually take information out of the networks. And for this, one way to attempt to do this is to create a model, right? So we create a generative model, a very, very simple toy model of what the data could look like. And then we ask the question of, is it true that in this model, can we actually detect the signal that we have in the model, right? And so the model here is very simple. I'm going to draw a random graph. Instead of being just a random 3-regular graph, I'm going to draw a graph that has some inherent community structure. And so the community structure I'm putting here is I'm going to draw a graph with n over 2 nodes, a total of n nodes. N over 2 nodes, I color them blue. N over 2 nodes, I color them red. And now I draw an edge in between 2 nodes with probability p if they have the same color, and with probability q if they have different colors. Okay. And so now I make q smaller than p. And so this graph, the blue nodes are much more connected in between them. The red nodes also, and there's less connections across. In particular, if q is 0 and p is 1, this is very, very easy. Like this has a very strong structure. And so if I ask you to find the colors afterward, it's very easy, right? But in general, for the other p's and q's, it's not clear how much community structure this actually has, right? In particular, it could be that there's a completely uncorrelated answer that would just have also a small cut, and right, like the issue I showed before. Okay, so now the game is I jumble everything together, I take away the colors, and now I ask you, can you find the blue nodes and the red nodes? Right? This seems like, what would you try? Well, I would try to find maybe the minimum bisection. Right, I would try to find the minimum bisection and say, one side of this is blue, another side is red. Of course, you will never be able to tell blue and red, but flipping the colors, there's no problem. It's just about the partition structure. But the natural thing to do is to just find the partition, the balanced partition, that has the least amount of edges that get cut. Okay, so now you can ask sort of the statistical question of when is it that works? Okay, you can ask this question. Turns out that the right regime to look at is when P is a constant times log n over n, and Q is another constant times log n over n. I mean, the actual expressions don't really matter. But it turns out that if, and essentially if and only if, this equation gets, so this equation here holds, then the minimum bisection coincides with the true communities. And you can show that if square root alpha minus square root beta is smaller than square root 2, then actually it is statistically impossible to find the true communities, right? So this is sort of the, indeed, minimum bisection is the best thing you can do. This is, right, it corresponds to the maximum likelihood estimator, to the maximum a posteriori estimator, and so on, depending which language you like to use. And it is the one that, you know, we know exactly, we can use statisticals, analysis, I guess maybe graph theory, right? But it's a statistical kind of argument. When is it that there's enough signal in the data, right? And this is the condition. However, we get faced with, you know, if we're doing data science in the sense that we actually want to, right? We actually want to do inference or do statistics on the computer, on big data, right? So on data that has more, like graphs that have more than, say, 30 nodes, much, much more than 30 nodes, but in particular more than 30 nodes or 50 or something. And there is a problem, right? Which is that minimum bisection is an NP-hard problem, right? So what does this mean is that, you know, I know with minimum bisection I can find these community structures, but this is actually a known hard computational problem. What does this mean? It means that, you know, it's very unlikely that there is an algorithm that can solve minimum bisection always. NP hardness says nothing, however, about what happens for most graphs, right? It could have been that because of the way I drew the graph, it's actually not hard, right? But at least we can't just go on, you know, you can't just go online and download a code that can solve every instance of minimum bisection efficiently, right? That, I mean, now we don't have such an algorithm, and most likely such an algorithm just simply does not exist. However, it turns out that you can push the theorem above and you can show that exactly in this regime in which you're interested in this, right? Exactly in the regime that you can find the communities, actually minimum bisection can be computed efficiently with high probability, of course. So this is like, I find this, you know, in this example, maybe it's not that striking, but I find this as a striking behavior that if we want to solve some kind of statistical inference problem learning, that the natural algorithm or the natural, you know, thing we want to optimize actually corresponds to a hard computational problem. However, in the instances that we care about, the problem actually is easy. And one of the questions I'm most interested in as a researcher is understanding, does this always happen? Is there a reason for this to happen? Are there examples in which it doesn't? When does this happen, right? When is it that there's this behavior where problems actually get computationally easy when there is statistical information to be learned? And so it turns out that we actually believe this not always happens. And here's a prototypical example of when we believe that this is not the case. So this is known as the hidden click problem, right? A very similar network type problem in which on one, I'm going to have two graph models. One of them is going to be just by g1/2. This is just a random graph model known as Erdős-Rényi graph, which, you know, has many, many decades now. And the idea is I just build a graph by every edge shows up with probability 1/2, right? All of them independent. Okay. I'm going to build another model of a random graph in which I do this, but I add a click. So what do I mean by this? I pick k at random. I pick a subset of nodes, of k nodes at random. Okay. I pick some k first, which will be sort of a design parameter. Then I pick k nodes at random and I connect all of them. Okay, so that's what we call a click in graph theory. Okay, and now the question is, can you detect this click? There's many, many ways of asking this question. You can ask, can you distinguish the two distributions? Can you find the click where if I planted it? These are at least morally equivalent. Okay, and now one way to try to answer the question of whether we can distinguish the two distribution is, I mean, a natural thing is to look at the largest click of this graph. Turns out we can do some, you know, some analysis. And you can show, and this is actually not so hard, that the largest click for the graph that wasn't tampered with is actually 2 log n, right? So this is the size of the largest click, and there's a lot of concentration of measure, right? You will see this number almost always. Of course, if k is bigger than this, the largest click in the one you plant is just k, because you planted that click, so it's there, right? So this means that if k is bigger than 2 log n, then, can you still see, or something seemed to happen with my screen?
We can still see the slide.
You can see?
Seems
Okay.
that you have something a bit frozen.
Let's see. Is it okay? It's moving?
You were going for the printer dialog, so everything is working again.
Okay, perfect. Yeah. All right. Great. Thanks. So now this means that if k is bigger than 2 log n, the graphs are definitely different, right? The largest click on the right is bigger than the largest click on the left. But again, finding the largest click is a hard problem in general. And so if we go see when is it that we can distinguish these things, we can go back to a paper from the late 90s, right? Including a colleague here at ETH, Benny Surakov. And this paper says that it exhibits an efficient algorithm and shows that it works when k is bigger than a constant times square root n. Right? This is very, very different from 2 log n. And essentially, this has had no improvement. Indeed, there's so much belief that this is difficult to improve over the square root n that this is actually used as what's called a reduction primitive. So people, essentially, like researchers, write papers where what they say is, your problem must be hard because if you could solve your problem, I could use the algorithm to solve your problem to solve this hidden click problem, and it would be an algorithm that would beat Alon, Krivolevich, and Surakov's algorithm, and we don't think that such a thing exists. Right? So this is how much belief the community has in the fact that this is a hard problem, and there's a lot of reasons to believe that, which I won't describe for now. So this shows a different story from what we saw before, and it's what I call the statistical-to-computational gap hypothesis, right? That some statistical problems, I'm using the example of networks, but there's many, many examples that don't involve networks at all, right? Where you have some notion of signal to noise ratio. This is sort of, in signal processing, this is the sort of the parameter that tells you how easy or hard your problem is, right? It's how much signal versus noise. You can think like 1 over the variance of the noise or number of samples, right? This in different communities, it has different names. But the more you go to the right, the easier the problem gets. So it's clear that, if your signal to noise ratio is just too low, the problem is statistically impossible. There's nothing you can do, right? And tools like in statistical lower bounds information theory and so on, they can tell you that indeed there's just no information. There's just no information in the data. You might by now we're quite good at developing algorithms, and we may develop algorithms that we can prove actually work when the problem is easy enough. So when the SNR is bigger than a certain other limit. What seems to be the case in some problems is that there's this region in between in which there is enough information in the data. Right? The data does have the information of what the right answer is, but we believe that there is no efficient algorithms to solve it. So this is what we call the hard phase, right? So the problem goes from impossible to computationally hard, which means effectively impossible in large data sets, and then to easy. And while traditional, information theory, statistical lower bounds, and so on, the tools it develops is, right, because it has ways of measuring information. So the tools it develops is to understand the statistical SNR threshold. Really the threshold that we should care about these days, by these days I mean as the data grows and we're interested in doing, in analyzing larger and larger data sets, we should really care about this computational SNR threshold. And so one of the things I'm very interested in is trying to understand how can we understand where this threshold is. What is it that happens in this hard phase, and so on and so forth, right? And so this gives rise to the question of what makes a problem hard, right? And it seems to be that what makes a problem hard has to do with how complicated, from either a viewpoint of complexity or geometry, is the possible solutions of the problem. Okay, I'm not saying very much, but one way is there is a way to try to understand the hardness, or at least make predictions about the hardness of the problem of learning the labels in community detection by relating it to a certain theory in physics. Okay? It's not clear exactly how as with what I said yet, but you can believe me, and maybe I'll say a few more words in the end. Right? So another thing is you can look at geometry of the set of solutions, or you can restrict yourself to certain classes of algorithms. Right? So these are 3 examples of things that one can do to try to understand. And I can talk like we had prepared a poll here to pick one of the three for me to talk about. I guess I still have 5 minutes, so I can talk 2 minutes or 3 about one of them. So if you want to put the poll, the audience can pick one, and I can talk more, or I can just pick one myself.
I think from what we see here, it would be best if you just pick one by yourself,
right,
so we can speed up and Sarah doesn't have to wait too long for her talk as well.
Perfect. So let me just say a few words about the one in the top. Okay, the 1 minute, 1 minute and a half explanation. So if you think about, right, if you think in terms of Bayesian statistics, right, let's put our Bayesian statistician hat on, then I can ask, what is the probability distribution of the node labels of being blue or red, given the graph that I'm seeing, right? This is now a probability distribution over, for each node, there's a 1 or minus 1. You can view this as sort of spins, right? If you think of each node as a particle, you can view the +1 as one spin and the -1 as another spin, and you identify it however you like with the blue and red. And so what you have is a complicated or potentially complicated distribution on spins where you think each node of a particle and it has a spin, right? This is what people in statistical physics call a spin system. And because in statistical physics, they're very interested in understanding phase transitions of matter, right? Like you can think of things like a solid going to a liquid or a gas, that kind of phase transitions, but there are others. And so they've been developing for many decades now tools to understand how complicated such distributions are. Right? There's models to understand magnetism, for example, that way, right? Magnetism would just be when all the spins tend to point the same direction, basically. Okay, and so you can borrow tools from statistical physics to make predictions about how complicated distributions are. And it turns out that they tend to be spot on as they make predictions of when the problem gets difficult, and they tend to be spot on. And in particular, they show that in a certain version of community detection with more than 5 communities, the problem starts having a computational gap, right? And then the other kind of tools show different things. There's a variety of problems that we believe have computational gaps, some of which have nothing to do with networks. Okay, and so just revisiting the example to give you a few more open problems, if graph theory is something you would like to think about. A very natural question now, after all I said, is what if it is true that I just give you a 3 regular graph, all right, or a d-regular graph in general, right? It did not come from the stochastic block model, it was just uniformly random. Can you actually find optimal bisections efficiently? So as d goes to, or at least a bisection that's as close as possible to optimal, right? As close as possible to the 11% in the case of d equals 3. So we know something, but a lot of it is conjectural. Like there's evidence that such things should be true, but we don't actually have a proof. And sometimes the evidence comes through physics, sometimes through other things. And so for d going to infinity, probably. Turns out that this corresponds to, can be related to a problem involving Gaussian random matrices. That's easier to understand. But still, easier, but still a very, still a tour de force to actually do this. But as d goes to infinity, probably. For fixed d, we're not quite sure. Some people think yes, some people think no. But now if you ask the question of, can you actually certify that no better bisection exists? If I give you a 3 regular graph at random with very high probability optimal bisection is of size 11%, but can you give me a proof that there's no bisection with less than 5% of the edges? Right? I can ask this question. And if I ask you, can you give me a proof that there's no bisection that cuts no edges? This is probably quite easy. All you have to do is find a triangle. And then if there's a triangle, no, this is not true. It's true for the other thing. But you can still, right? All you have to do is to prove that that the graph is connected, which is much easier. And if it's connected, I cannot split cutting 0 edges. But turns out that we believe there's a big gap in the problem of certifying. So instead of 11%, you can maybe certify, and I don't remember what the numbers are like. They're like maybe 5, I don't remember, but there is a gap. We believe there is a gap. Okay, but again, it's hard to actually show these things. And yeah, on these types of things, there's just countless many open problems. Okay, so I'm running out of time. So I'll just right here, by now I think I made clear that there's a lot more that we don't know than what we actually know. And even specifically to understanding these computational thresholds, there's a lot more that we don't know that we know. And I think that the biggest question from from the mathematician viewpoint is we have all these ways of predicting, all these heuristics, all these versions of what makes a problem hard. Can we actually show some kind of universality or equivalence between them, right? And we, at the moment, we're still, I think, a little far from this. Okay, thank you so much. And yeah, hope I didn't take more time than I was supposed to.
Yeah, thank you so much for your presentation, Afonso.